Okay, let's get started. So last time we implemented the attention module and checked the dimensions. So let's connect and okay, so just to review really fast. So in transformers, we have the attention module and some other things like residual connection, RMS norm, etc. But at the end of each transformer block, we have the MLP layers, and it had this specific structure. So input X is one of the token embeddings and gets routed to two FC layers, fully connected or linear layers, and CLU takes input from the second linear, and they get element-wise multiplied, and then the result gets routed to the third linear layer. So we implemented that together, check the dimensions, and look at the flops. So in dimensions, the flops is quadratic, and in sequence length, the flops is linear because in the MAP layers, the tokens do not communicate. And we actually measured the runtime to compare against our flops analysis. In real life, runtime does not coincide with flops. There are many other things that comes into play in runtime. For example, if you're using GPU's GPU memory bandwidth, and how many times you are moving data from CPU memory to GPU memory, all that information and number of streams in GPU processing, and many technical details. But it was enough to see the linear and quadratic relation in this case. And the most important component in transformer block is the attention layer. And input comes in sequence, and we compute the query, key, and value activations, and we auto product Q, query, and key, and we also impose a causal mask and apply softmax, and this output of the softmax, we call it attention score, and it gets multiplied with the value vector, and the output gets routed to another linear layer. So we have actually four matrices, WQ, WK, WV, which typically increase the dimension from the input dimension to some higher dimension. In this case, in our example, this was 2 times the dimension. And the output matrix projects that down projects from head dimension to the original dimension. So dimensions get preserved before and after attention. So we implemented the core attention module together last time. So input comes in, and we apply these 3 matrices and the output query vector, key vector, value vector is of size, batch size, sequence length. This is number input tokens, and head dimension. And we're supposed to auto product query and key. So as you can probably see, in order to take the auto product between query and key, you need to transpose the key vectors so that the outcome is of size batch size times sequence by sequence. Right? So you need to swap the dimensions for the key for these two guys, sequence, head dim. They need to get transposed so that once you apply matrix multiply, the output is of size sequence by sequence. And then we talked about this in the class. You normalize this by by square root of the head dimension. And then simply you take the softmax, and that's the attention score. And you take the attention score, and like in the figure, you multiply by the value vector. And that's the output. This is still batch size by sequence by head dimension. We need to down project them to the original dimension, which was just dim. So it gets multiplied with the down projecting matrix W out. And that's the result. So we did this together last time, right? Okay. Let's check the dimension. So here we're going to create some random matrix with batch size 2, sequence length of 10, dimension 64. Head dimension, this time we're just going to keep it at the same. And we have some input tensor. So you can think of these either as the raw input, which was projected using some word embedding matrix, or output of the previous transformer block. They're all going to have the same dimensions: batch size, sequence length, and dimension. So upon receiving this input, each transformer block is going to compute the attention, and let's check the shape. So input shape is batch size 2, sequence length 10, dimension 64. Output of the attention is the same. Size of the attention map is batch size by sequence length by sequence length. Right? Okay, so I think we stopped here last time. And let's complete this portion. So here, we're going to check the complexity of the attention module and draw it in terms of the sequence length and the dimension. So here, we have already provided for you the flops for the linear layers. So we have 4 linear layers, right? WK, WQ, WV, WO, right? We have 4 of them, and each matrix sequence length times dimension times head dimension. Right? Per each token separately, we're going to do matrix vector multiply and times 2 for the flops because we want to count each multiply and add. And we have 4 such matrix multiplies. And to do is the attention part itself. And let's neglect the softmax because it's an element-wise multiplication, element-wise operation. It's very cheap. So just to clarify, this portion is already provided for you, you receive input of size, batch size by sequence times sequence length by dimension. The matrix multiply here and here. This part is already computed for you. You need to compute the flops, ignoring softmax for this portion. Is this better in the back or this one? 1, 2. Huh? Okay. Anyone finished? Okay. Okay, so you have computed the key value query matrices, activation vectors, and how about the attention score? So first component is taking the query and doing matrix multiply with key transpose. So this is size of query and key, these two dimensions are swapped. End result is, if we ignore the batch size, that's sequence by sequence. And so output is a 2D matrix of size sequence by sequence. And each element in the matrix requires taking inner product between two vectors of size head dimension. Where is it? Yeah. So output is sequence by sequence, right? Each element in the matrix is inner product between two vectors of size head dimension times 2 for adds and multiplies. And what follows after? This we can ignore, this we can ignore. Here, we take the attention score, multiply by the value vector. Output size is sequence by head dimension. So we take this guy of size sequence by sequence, multiply by a vector of size sequence by head dimension. So output sequence by head dimension, sequence by head dimension, and individually we need sequence length amount of computation. Add them together and see what happens. Okay, so as expected, in terms of sequence length, we need quadratic number of flops. It's intuitive because we're building our attention map upsize sequence length by sequence length. And in terms of dimensions, it still looks quadratic. Okay, let's actually measure with the wall clock runtime. It's going to repeat 100 times and average the results. Okay. I don't know where this peak came from, but looks quadratic to me, except this guy. So if you're not happy with this result, try to increase this with 1,000 or 10,000. Okay, so let's try to build some intuition on these attention maps. So we have some helper functions. One is what are we plugging in? So this is just a helper function for computing the attention score. This is a helper function. If you look at it, given some string input, it builds a histogram of all characters, all small letter characters. So you convert each letter to a small letter. So there are 26 characters in your universe, and it computes the frequency of each characters from A to Z. Okay, so here is some example sequence of tokens. I love machine learning and deep learning, and so we're going to compare two different attention. So one is based on the location of each tokens, and to build the Korean key, we're going to do the following. So here, we're going to create some index array starting from 0, 1, 2, all the way to number of tokens, divide by 2. And then we're going to compute sine and cosine of x. That's going to be the key and the query, same thing. So this input, you can think of this input query and key to be sensitive to the location, relative or absolute location in which location that encodes the ordering of where it came in the sequence of the tokens. So this is purely sensitive. It only matters, so this query and key is only a function of the location of the corresponding words. And we're going to compute the attention score and visualize the result. Second thing is we're going to try to capture similarity between tokens. How are we going to do that? We're going to convert each token, convert it to a histogram of all characters. So we're going to count the histogram starting from A, B, C, all the way to Z. And we're going to say two tokens are similar if these two histograms are similar. And we're going to say two tokens are different to some degree based on how much they differ from this histogram of alphabet characters. We're going to build Korean key based on this character frequency and visualize attention for each two cases. So first one is position sensitive, key and tokens, key and query. Case 2 is alpha frequency sensitive, or you can interpret it as semantic similarity. So let's plot the results. So like expected, you get high attention score for the nearby tokens. So we have high attention scores for example, for machine, the tokens that come near, because we have this position sensitivity encoded in the query key. And for the semantic attention, it takes the outer product between two character level histograms. So let's see which ones have high similarities. So for example, learning is highly similar, has a high attention with learning itself, and also learning, because they have same character frequency. So we have two same words that appear in the sentence. And do we have any interesting other examples? Okay, how about machine is similar to learning, then it is similar to love. Why is that? Because there's N here that matches, I here that matches. So N occurs twice in these two tokens, and there's I and there's A, and here compared to love, there's only one letter that matches. So something like this. So this attention score is sensitive to the character level frequency. So this is what we would like to see when we have multi-head attention. So we have different attention heads, and supposedly each attention head is sensitive to different aspects. One is more sensitive to position, one is more sensitive to its semantic meaning, and etc. Okay, so we talked about this in the lecture as well. So in order to do autoregressive generation, we need to enforce the causal masking. We want to prevent tokens from looking into the future, because during training, that's fine. You can look into the future, everything's static. But during inference, you're going to generate one token at a time. So if you do that in that scenario, you cannot look into the past. You can only attend to what is previously generated. That's why you need the causal mask. So we have some helper functions. So if you're not familiar with these functions, you can hover your mouse or just go to Torch API. So it builds an upper triangular matrix with ones above diagonal. So this creates a matrix of all ones, and this flag gives you a upper triangular matrix with everything below diagonal all 0. And here we're going to mask it so that sorry, I said it backwards. So here, upper triangular matrix with ones above diagonal, and we're going to look at all the ones, replace it with negative infinity. So we're going to create a mask where all the diagonal entries and all the entries above diagonal is set to negative infinity. So let's visualize it. So this is the end result. So this shows entries that is not equal to negative infinity. So given this mask, so why is it okay? So why is it set to negative infinity? So we're going to apply this mask before we take the softmax. So first thing is taking outer product of query and key. It gives you unnormalized scores. And then given the scores, we're going to add in this mask, which has negative infinity. And then we're going to take the softmax after we apply this mask. So these entries are going to have all zeros after we apply softmax. So for example, okay, so there's a to-do here, and just to give you an example, this query 3 can attend to everything until itself, but not past itself. And query 1 cannot attend to all other future tokens and etc. So the exercise here is this is the same attention class that we implemented, but here we have one extra step. So here it's going to receive a mask of size, batch size, sequence by sequence, or it could be sequence by sequence, because we do not need to apply different mask for different batch elements. So depending on use case, which is just simpler to just receive an input of size sequence by sequence. So rest of them all the same. As soon as we compute the outer product and normalize, we're gonna apply the mask by adding negative infinity to some of the entries, and then apply softmax and multiply value matrix, then output. So let's implement this part and check the shape and check the input output attention size shape and etc. So here we're going to call the helper function to generate the causal mask, and then call this attention method with the given mask. All done? Okay. So our input was, what was the size of the input mask? So it generates a mask of size sequence length by sequence length. It makes sense to do so from outside because we're not going to apply different mask for each different batch elements. So if the mask shape is of size 2, then we need to expand one dimension so we can add it for all the batch elements. So in Python syntax or NumPy syntax, it does what's called broadcasting. So based on context, it automatically applies this mask for all dimensions. But in order for that to work, you need to expand the dimension for the batch. Okay, so all is as expected, right? So before and after attention, the input shape is preserved. Attention size is batch size by sequence length by sequence length. Okay, so let's talk about multi-head attention. So within a single transformer block, we learned in the class that we're going to have multiple attention heads. So we're going to make extensions to the attention class so that it can support multiple heads. So now there's an additional input here called n head. So that's the number of heads that's newly added. And if you look at the dimensions, these matrices, WQ, K, V, O, is of size dimension times, this used to be times head dimension, but now it's number head times head dimension. And output down projects them to a single, not single dimension, but to dimension. Okay, so you're going to receive input of size dimension, up projects them so that it's of size number of heads times headed dimension, and you're going to repeat the same procedure. At the end of the day, the final output is going to be the same, so it's of size batch size by sequence length by dimension. Okay, so you're given pretty much the same code template. This guy is newly introduced, and looks like there's an unnecessary helper UI that's going to prevent me from scrolling left. Okay, so here, once you apply these masks, matrices, now your output is of size batch size sequence length by number of heads times head dimension. And you're going to do some massaging, and the result should be of size batch size, number of heads, and sequence length and head dimension. And we used to ask you to implement this whole thing, but it took too much time, so we're going to ask you to do massaging only. And then after you do this massaging, then rest is straightforward and it's given to you. So given a query of size, batch size, number of heads, sequence by head dimension, you're going to multiply with a key which has the same dimensions but you're going to transpose 0, 1, 2, 3. This one and this one, you're going to swap the order with transpose of 2 and 3, so that the output is of size, batch size, number of heads, sequence by sequence. Does this make sense? So we're going to take this tensor, do some massaging so it has this following dimension, so that once we do matrix multiply, inner dimensions are going to commute and produce an output of size, batch size, number of heads, sequence by sequence. After then, same thing, normalize, add the mask, compute softmax, and do matrix multiply between attention score and value. And here, let's see what's happening. So attention score is of size, batch size, number of heads, sequence by sequence. And value, the dimension of value is batch, sequence, number of heads times head dimension. So okay, let's look at it together. We're going to multiply this guy with this guy. And sorry, I got confused a little bit. So this is of size, batch size, number of heads, sequence by sequence. Value is after reshape, and we're going to be batch size, head. So we're going to look at this guy and this line here. So multiply this guy with this guy. Batch, number of heads, sequence, 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 number of heads. So after we multiply these two, the output is going to be batch size and head, number of heads, sequence, and head dimension. Because this dimension here is going to commute with this guy, and we're going to get an output of sequence by head dimension. Okay, this guy commute with this guy. So output is batch size, number of heads, sequence, head dimension, and the newly added portion is this part. We need to get the output of size, batch size, sequence, number of heads times head dimension. So we're going to do some reshaping. So once we get this matrix, we're going to reshape it so that it's of this dimension again. Batch size, sequence, number of heads times head dimension. After then, why are we doing this? Because we're going to get this W out matrix and multiply output so that we can come back to the same dimension, original dimension, which is of size, batch size, sequence, and dimension. W out was of size, number of heads, head dimension, and dimension. So this down projected. So this reshaping is necessary so that we can multiply with this out matrix. Number of head times head dimension times dim. Right? It's going to commute with this dimension here and down projected to the original dimension. All right, so just to help you before you implement anything, we provided some small tutorial here that could be useful. So there's a reshape and transpose. How are they different? So let's suppose we have this 2x3 matrix. And if you do a reshape to 3x2, we're going to get 1, 2, 3, 4, 5, 6. So it reshapes it in row major format. On the other hand, if you do transpose, you get 1, 4, 2, 5, 3, 6. It does mathematical transpose. So think about how they are different. And once you finish implementing, let's check the dimensions. So we're going to have batch size of 1, sequence length of 10, dimension of 64. That's the input dimension. Number of head is 8. Head dimension is, what is this? Head dimension is 8, right? So dimension is 64. 64 divided by 8. Previously, this used to be twice of dimension, but in this exercise, they are of the same dimension. And we're going to create a random tensor. So this is the input to the transformer block, batch size, sequence length, dimension. So 1 by 10 by 64 tensor comes in. You apply attention, generate mask, and apply attention. And so this now is going to be multi-head attention, right? We have this additional input for number of heads. So once you apply multi-head attention, we're going to check the size. So yeah, so why don't you try and implementing this massaging part. Okay, so just to, okay, what is the expected output here? So sequence length is 10, number of head is 8, input size is 1 by 10 by 60, 1 by 10 by 64. Output size is supposed to be what? Right, same as input. 1 by 10 by 64. How about the attention score? What is the expected shape? One by 8 by 1 by 8 by 10 by 10. Yes. So we have this attention map for each head separately. All right, so let's implement this portion. Okay, just to let you know, in the previous year we asked you to implement this, but nobody was successful during class, so we just gave you the answer. In case you're a beginner to implementing things, you might be wondering, why are we doing this complicated reshaping, transposing? Why can't we just use for loops? That's easy, right? So yes, it's correct to use for loops, and you will get exactly the same answer. But if you vectorize this code, so vectorize meaning doing without any while loops, for loops, then it's going to be much faster to compute. Because CPUs and GPUs can parallel process matrix multiplies. So if you write your code only using matrix multiply vectors or element-wise operations, so if you chain these existing functions and do not use any for loops, then it's easier for machines to interpret it in a way that it's faster to compute. So we're doing this complicated thing just to make it run fast. Okay. Anyone have finished? Okay, most of you. Okay, let's look at the solution. And there's no one correct answer. There are many different ways to do this. So this is one example solution. So query key value is upsize batch size. Sequence number of heads times head dimension should be batch number of heads sequence head dimension. So first, we're going to reshape this matrix. So it's upsize, batch size, sequence. We're going to break this multiply with reshaping and create an additional dimension. Okay, now the number of dimensions match, but this is not the order that we want. We want sequence head dimension. So we're going to transpose 1, 2, so 0, 1, 2, this one, and this one, we're going to swap the order. So if this part is unclear, just go back to this tutorial and try to understand how the outcome can be different if you use reshape versus transpose. Okay, so this was the end of the attention lecture. And let's see. So, like we briefly talked about in the lecture, in modern implementation, you need much more than this. You need residual connection, pre-norm, RMS norm, and SWI glue, MOE, LoRa, all these things. So that's what we're going to do. Oh, and most importantly, positional encoding. So in the lecture, we saw. Is it connected? We saw that the tension is permutation equivariant. If you swap the order of different tokens, you will get the same result, but the order swapped in terms of QKV. So it's permutation equivariant. But like you already know, in natural language, the relative order of the words matter a lot. So we're going to inject some positional information into the input feature. Simplest way to do this is to augment the word embeddings with actual positional information, 1, 2, 3, 4, 5, 6. So augment the dimension by 1. Simplest hack you can do. So this is absolute positional encoding. So just take your word embeddings and encode the positions and concatenate it. But however, this is not translation invariant, meaning let's say I add in a word in the front here. Say the token is HMM. So now the positional index shifts by 1, but carries the same information, pretty much the same information. But if you shift the position of a sentence by 1, different tokens will have different positional encodings. It will get shifted by 1. So in the perspective of a machine, it just sees an array of numbers. But this now is just additional combination of the numbers to learn. But for us humans, it's natural. They mean the same thing. So it leads to poor generalization performance. It's just one additional example to fit. But if we could teach the machine or reparameterize this so that we can indicate these are pretty much the same thing, and you don't need to learn this completely from scratch, then leads to better generalization. It's better use of the training data, in other words. So there are many other different ways to encode the relative positions between two tokens. This is the most famous one, called RoPE. So it's rotary positional encoding, or RoPE. And the idea is pretty straightforward. You take your key and query vectors, slice it by pair. So you take each 2 consecutive dimensions and apply rotation. So suppose in your example, so here's an example. We have this sequence of tokens, enhanced transformer with rotary position embedding. So enhanced token is in position 1, transformer token is in position 2, etc. So we're going to take a pair of the dimensions and apply a rotation proportional to the position of the vector within this input sequence. So, for example, features Q and key, query and key at positions N and M. We're going to apply the rotation for each features. So take the query feature, and let's say this token appeared in location N. We're going to apply a rotation proportion to N, and take the key vector which the underlying token appeared in location M. We're going to rotate it by amount proportion to M. So once we rotate these query and key vectors for all locations in the input sequence, we're gonna when we compute the outer product of the query and key, we take the inner product between the rotated features. So suppose there is some translation in the relative location of these tokens in the sentence. So suppose we observe exactly same combination, but even in different order in the sentence. Then, if you compute the normalized attention score first, that's inner product of the rotated feature by amount N, rotated key feature by amount M. And in another sentence, if the exact same combination appears in different order, they get rotated to some degree that is translated by index T, and by property of location, these inner product ends up being the same. So that's the core idea of RoPE. In detail, we slice 2 dimensions each, apply rotation, move on to the second pair, apply slightly different rotation, and etc. So what is slightly different? So for each feature dimension, we slice it into two-dimensional consecutive pairs or chunks. And in addition to this position sensitive rotation amount, we multiply by this theta, which is sensitive to the location in the feature index. So the rotation amount is actually, do I have an equation somewhere? It's actually m times some data, where this data, so m depends on the location in which it appeared in the sentence, so token index. Theta depends on location of the feature dimension, so which location in the feature index it came from. So this data is mathematically, that's some base raised to the power of negative I over d prime. So I is which index it came from in the feature dimension. D is the total dimension here divided by 2. So this rotation is sensitive to two things. One is there's a multiplicative factor m here, which depends on which location it came in the token index. And theta is dependent on which pair it was, which location in the feature index. So it's sensitive to token index and feature dimension index. Okay? So this happens before we take the product product. We receive some input, compute the query key value, rotate these query and key by something that's proportional to the index, token index, and proportional to the feature index. Okay, so that's the idea. Is there something you guys implement? Yeah. Great. So here is your to-do. So this is the RoPE class. And initializer base is given is 10,000. And you're supposed to compute the data. And data is this guy here. It's base raised to minus I over d prime, where d prime is head dimension by 2, divided by 2. So if you call the function, it's going to return actually the cosine and sines of the angle, rotation angle. So position IDs is given in the call signature. So that's the location of each tokens. So this is a consecutive number. So let's look at the size. It's batch size, sequence length by 1, and the data from this compute data function is batch size 1 by head dimension over 2. So we're going to multiply the position indices with data, and that's going to end up being batch size, sequence length, head dimension over 2. And given these numbers, we're going to compute the cosines and sines. Why? Because we're going to apply rotation. So in 2D, what is the 2D rotation matrix given an angle theta? It's a 2D matrix. So you're given a 2D vector, you're going to apply a 2D matrix. What is a 2D matrix? Yes? Cosine theta. Is that right? Okay, let's just look it up. 2D rotation. Okay, so we're going to take this guy and multiply the 2D vector. And this angle here is given to you. That's the Fricks here. That's m times theta, where theta is given by compute data. So this call signature gives you cosine thetas and sine thetas. And you have this apply rotary positional embedding function, which you're going to implement partially. So given query key cosines and sines, it's very simple, right? So cosines are, like I said, m times theta I. Sines are m times theta i's. And the end result is batch size 1 by sequence, head dimension over 2. And this portion is what you're going to implement. It's very simple. You should slice the queries and keys, take two consecutive numbers, apply the 2D matrix, 2D rotation matrix, move on to the second pair, apply the 2D rotation matrix. Now look at the consecutive pair again, apply the matrix, etc. So pretty much everything is given to you. And when you finish implementing, we're going to do some testing. So we're going to create a rope with head dimension 64. And we're going to supply positional indices from outside. So it's just a number from 1 to 0, 1, 2, 3, etc. Consecutive numbers, which is supposed to indicate location of the token in the given sentence. And we're going to compute the cosines and sines and check the dimensions. And also, we're going to visualize the rotation frequencies. Let's first finish implementing. So slice the querying key in terms of pairs, consecutive pairs, apply 2D rotation matrix. Okay, so it's easy, right? So you just slice it in pairs and take the query and so this is the sliced pair. You apply cosine minus sine, right? That's the 2D matrix, cosine minus sine. Multiply inner product with the vector. Second guy, sine and cosine. And same thing for the key. You apply the same rotation, but for the key pairs. And unfortunately, the time is up, so we'll pick it up from next time. Thanks.